The ratio test is another convergence test, and the way it works is really interesting. It's also very easy to apply. So we're going to let this series, a sub k, be a series with positive terms.
Check the display on your iPhone for the answer.
All right, if a sub k is a series of positive terms, let the limit as k goes to infinity, a sub k plus 1 over a sub k. So what you're doing is you're taking the quotient of the term divided by the previous term. And suppose this equals some number r. And there's some things here with whatever r is. If r is between 0 and 1, now r is not going to be negative because these terms are positive, but r could end up being 0. So if r is between 0 and 1, and I'm including 0 in this, the series converges. If r happens to be greater than 1, the series diverges. And unfortunately, if r equals 1, we can't say. We just say the test is inconclusive. Now, the outline of the proof, or how it works, I'll just say proof outline because I'm not going to go through all the messy details. But you would say something like for large values of k, that'd be those k values that are greater than some mysterious n. We would have ak plus 1 over a sub k is approximately r, since the limit is going to r. For large values, we're going to be close to r. So ak plus 1 is approximately r times a sub k. These are large values of k. And if we look at the series, a sub k, doesn't really matter what it starts, but in this particular situation here, I'll start it at 1. But you're going to get up to a sub capital N, and then we're going to let another series start, which is the tail end of the a sub k, if k goes from this capital N plus 1 to infinity, a sub k. And so for these large values of k back here, I'm going to replace a sub k plus 1 with rak. So I'll have a1 plus ... plus a sub n plus, now let me put this in parentheses, we'll have a sub n plus 1, a sub n plus 2, blah blah, ... goes on forever. Now I'll put my little approximation sign. So this a sub capital N plus 1 is close to r a sub capital N. This one right here is close to r a sub capital N plus 1, and that goes on and on and on. But now I can apply it again to those large terms. I'll still have r a sub n, but then I'll have this a sub n plus 1 is approximately r sub a sub n, so I'll get an r squared a sub n, and then I'll get an r cubed a sub n plus, and that will go on. Well, this here then is equal to a1 plus ... plus a capital N plus, now what I'm going to do is factor out an r and an an, and that will leave me with 1 plus, if I take it out of here, I'll have an r, then I'll have an r squared. Well, in here, this is the crucial piece here. We know that this piece will converge. So let me write that down. We know the series will converge when r is between -1 and 1. Because it's a geometric series. So we've already been through that 100 times. So when r is between -1 and 1, the series will converge. However, since ak is greater than 0 for all k, we have that the series converges when r is between 0 and 1, but I'm including 0 because it will converge when r is equal to 0. Now, most of the other stuff is because of this kind of thing here. If r is greater than 1, we know this series diverges. No problems. When r equals 1, I can't do this here. I cannot plug an r equal 1 into this. So this series, well, it's going to diverge. If r is equal to 1, this is going to equal infinity, and that r won't count there, and it will probably diverge, but I cannot say for certain since I can't plug it in here. So we're going to leave it at that. This is what I'm looking for. If you get 1, you go, try again. If you get something like this, you're good. If you get r greater than 1, you're good. It's just that r equals 1 we can't do anything with. So let's do some examples. You'll find this series is practically, this kind of test is practically fun to do. You'll see. Now I'm going to try to pick series for the beginning that won't yield some integration, and this is one of them. We don't really integrate factorials because these numbers are not continuous. This is just k times k minus 1 times k minus 2 down to 1. But I am going to use the ratio test then. And that's where I compare a sub k plus 1 over a sub k. And now you have a fraction. This is supposed to be the limit, actually. And so let me rewrite this. This fraction over here, 2 to the k plus 1 over k plus 1 factorial times, this fraction flips, and I'll get k factorial all over 2 to the k. Now there's a lot of canceling that goes on. For instance, 2 to the k plus 1 cancels out the 2 to the k, and I'll be left with just a 2 in this spot up here. Down here, I can take out all the k factorial, and it will take out all the terms before k plus 1. So I'm looking at the limit as k goes to 0, k goes to infinity of 2 over k plus 1, which does equal 0. So the series converges. And that's by the ratio test. A slightly different one, a little bit different. Here I'm going to have not 2 to the k, but k to the k power. And on the bottom I have 2 to the k. Now you could probably tell that this is going to diverge just by looking at it. This is going to outrun this without a problem. In fact, I'm not even sure that the limit of this goes to 0. But let's see what the ratio test says. So I'm going to take the k plus 1th term divided by, well no, the k plus 1th term, that's still part of it, divided by the kth term. And I'll do the same thing as I did before. There's going to be fractions all over the place. So I'll have k plus 1 to the k plus 1 divided by k to the k times, and this bottom fraction will flip, so I'll get 2 to the k all over, I think I made a mistake here, Down here should be 2 to the k plus 1. And then I'll have over k to the k. Now the canceling is a little bit weirder than before. This 2 to the k still cancels most of the 2's out of there. But right here is a difficult situation to work with. Let me rewrite that. So the 2 that's here, I'm just going to pull it out. It's not necessary. But now I'm going to have k plus 1 to the k plus 1 all over k to the k. So let's see what happens there. Well, I can break this up in the following format. What I'm going to do is break it up into k plus 1 to the k times k plus 1, and that'll be over k to the k. I'll rewrite this one as one fraction, so I'll have that piece k plus 1 over k to the k, and then I'll have a k plus 1 out there. Now in here I'm going to rewrite this fraction. So if I do that, I'll have k over k plus 1 over k. That'll be to the k power times k plus 1. That equals the limit as k goes to infinity, 1/2. This one right here will be 1 plus 1 over k. And that'll be to the k power times k plus 1. Now right here, you ought to know that this piece by now, with all the things we've done, that piece right there is going to go to e to the 1 power. Of course, the 1/2 really doesn't matter. But this piece here is going to infinity. So if you've got this piece and this piece approaching a number, this piece going to infinity, the entire limit is infinity. So the series diverges. Let's try another example. Maybe the numerator was too much here. We're going to try to soften up the numerator a little bit and look at k equals 1 to infinity, 2 to the k, all over k to the 4th. So I'm going to do the same thing I did before, the ratio test. This probably would not be terrible with L'Hopital's rule, or I'm sorry, with the integral test. But I think this might be, you'd have to do integration by parts. I'm not so sure it'd be so pretty to do. So maybe it's wrong of me to recommend that it is even trying. So I'm going to go to the ratio test and see what it tells us. So as before, I'll take the k plus 1th term all over the kth term. And then figure out these fractions. I don't know why I keep forgetting that, but so this fraction will be 2 to the k plus 1 all over k plus 1 to the 4th times k to the 4th all over 2 to the k. And I'll play the same game as far as canceling. I'll get rid of most of the 2's. Again, in fact, if you want to bring that 2, you can take the 2 out front of the limit because it's not affected by this limit in any case. But what I have left is k to the 4th over k plus 1 to the 4th. Now, you can go and do L'Hopital's rule here if you want to, but in fact, this is 2 times the limit as k goes to infinity. And what I'm going to do, I'm going to sort of multiply out the denominator, but I'm not going to do it all the way. The denominator will be k to the 4th plus other things. I really don't care. All I care about is the highest power, and that's k to the 4th. Something like this, as k goes to infinity, this piece equals 1. Well, since 2 is bigger than 1, series diverges. This one I'll have k factorial to the third. Anytime you see a factorial, forget about the integral test. That's not going to happen. You're going to have to use some other test, and this is the most likely one. So I'll do my ratio test again, and I'll take the k plus 1th term. So you got to be careful with how you write this. If I replace k with k plus 1, then I need to do k plus 1. That's the thing that's being factorialed, and then it's being cubed. The denominator is even more fun. In there, you're going to replace k with k plus 1, so you're going to have 3 times k plus 1. But the 3 was part of the factorial too, so I'm going to put this, and then that. Actually, I don't need the outer parentheses. I can get rid of this, so I don't need that, and I don't need that. All of that is going to be divided by the kth term, so I'll have k factorial cubed slash 3k factorial, like that. So let me rearrange my fractions as normal. Here, make sure you multiply the 3 through. This will be 3k plus 3 factorial. And then I'll have 3k factorial divided by k factorial. And that thing will be to the 3rd power. So let me do some rearranging of things. Here, since this is to the 3rd and this is to the 3rd, I can combine those and get k plus 1 factorial all over k factorial. That'll be raised to the 3rd power. Alright, so I've got this combined to the 3rd power, and then I have this kind of stuff here. 3k factorial. I think I'm going to mix that with the other factorial, so I'll get 3k factorial divided by 3k plus 3 factorial. I'm figuring a lot of students will make a mistake on this portion of it and not do it correctly. Now, let me go ahead and do some canceling in there of the limit as k goes to infinity. So k plus 1 factorial over k factorial. We've done this canceling a billion times. That'll just be k plus 1, but it'll be to the 3rd power. And over here, I'm going to get 3k factorial. Now I'm going to count down. I'm going to start at 3k plus 3. And then I'm going to go to 3k plus 2. And then 3k plus 1. And then finally 3k factorial. So cancel and cancel. Now this is 3 individual pieces. When I multiply them out, I really don't care about all of the terms in that. All I care about is that I'm going to have k plus 1 cubed is going to be k cubed plus lower power things. The denominator, if I multiply 3k times 3k times 3k, I'll get 27k cubed plus, and there'll be other stuff in there. None of that other stuff matters. The fact is that this limit depends on the highest power. So if I look at the coefficients of the highest power, I'll get 1 over 27. There's a million ways you can do this. You can use L'Hopital, or you can just recognize and remember that you simply take, if the power is the same in the numerator and denominator, the highest power that is, then you simply take the quotient of its leading coefficients. So this equals 1 over 27. That means the series converges. Now consider this series. We know the series already diverges. Now, if you were to try to do the ratio test with these terms, the ratio test would do the following. I would do 1 over k plus 1 divided by 1 over k, and that'd be, and once again I keep forgetting that limit. That would be the limit as k goes to infinity, k over k plus 1, which equals 1. So the ratio test is inconclusive. But we can use the integral test to do that one anyways. 1 over x ln of x. So we have another test that will handle this one. We call it the root test. Well, it will handle some. I don't know if it'll handle that one, but this is another test that will help us. Let a sub k have non-negative terms. That's a new one. And let's see, rho equal the limit as k goes to infinity, the kth root of ak. Now, this is interesting. This may seem really bad, but you'll find out there will be a certain variety that are homemade for this kind of a test. And we have kind of the same things as before. If 0 is less than or equal to rho is less than 1, the series converges. If rho is greater than 1, the series diverges. And the last one, just like the previous test, if rho equals 1, the test is inconclusive. So, and the way this kind of works is just like anything else. This will just be an outline like every other proof that I'm doing here. You're going to have, when k is large, so you can imagine that k is greater than some mysterious capital N. The kth root of a to the k is roughly equal to rho. So that means a to the k is roughly equal to rho to the k. So your series would look something like this. You'd have sum of a sub k, and it will equal some initial terms, a1 plus dot dot dot, and you get up to a sub n. But then you'd replace the ak's by rho to the k. Well, let me write it first. K, when k is n plus 1 to infinity, a sub k. This is approximately equal to a1 plus dot 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 an plus, then I'm going to replace a sub k with rho to the k. And right there again, we have a geometric series. This piece is going to converge when rho is between 0 and 1. Remember, I'm not talking about negative values for this particular series. This was non-negative. And we didn't have to use positive because I wasn't dividing by a series, so I'm allowed to get away with 0 in this case. So it converges when rho is between 0 and 1, including 0. Obviously, it diverges when rho is greater than 1. And then, as before, when rho equals 1, we don't know how to add it up because we want to go 1 over 1 minus rho, and I can't plug that in. So rho equals 1 is inconclusive. Let's go ahead and take a look at some examples. Now this series, at first look, it's horrible looking. K equals 1 to infinity, and I'm going from k to the k over 2 to the k, which we've already done. Just rewrite it like this. K equals 1 to infinity. Rewrite it as k over 2 to the kth power. Then when I do the limit as k goes to infinity of the kth root of that, k over 2 to the k, well, the kth root cancels with the kth power, and you're left with the limit as k goes to infinity of just k over 2, which equals infinity, and that proves that the series diverges. In fact, anytime you see a series that has powers, you have a shot with the ratio test. So this one here, I'm taking to the k squared power. So then when I do the limit as k goes to infinity of the kth root of 1 plus 3 over k to the k squared. Keep in mind the kth root is like 1 over k. So when I take k squared times 1 over k, I'm going to equal the limit as k goes to infinity, 1 plus 3 over k to the kth power. You can go ahead and use L'Hopital for this or whatever it is you want to use, but I happen to know that that converges to e cubed, which is greater than 1. So the series diverges. Let's see what we have now. We have k over e to the k. And to be honest, the kth, well, let's go ahead and take a look at it. The limit as k goes to infinity, the kth root of k over e to the k. Well, I'll get this. So if I'm using the root test, the k will cancel with the exponent on the e to the k. But then I'll be left with k to the 1 over k divided by e. Of course, the e doesn't matter. I'll pull it out front. We have done k to the 1 over k before. I will leave it to you. This guy right here. Use L'Hopital. Use L'Hopital's rule to show that that equals 1. So this limit will equal 1 over e. And 1 over e is less than 1. It's also positive because e is positive. The series converges. I personally would have used the ratio test on this one. So alternatively, the ratio test gives us the limit as k goes to infinity. So I'm going to have k plus 1 over e to the k plus 1 divided by k over e to the k. And this is going to equal the limit as k goes to infinity, k plus 1 over k times e to the k over e to the k plus 1. Well, the e to the k's will cancel pretty easily, so I'll be left with 1 over e just like before. And this limit's very easy to do. It's a one L'Hopital step problem to get that to be 1, and you'll get the series converges as well. And this will be, the k power kind of tells you it's time to use the ratio test. So when you look at the limit as k goes to infinity of the kth root of that, so I have k squared over 2k squared plus 1, and that thing is to the kth power, as with all the other ones. The k's cancel, the exponent and the root, and I'll have the limit as k goes to infinity of k squared all over 2k squared plus 1. It's a two-L'Hopital problem. If you want to do that, you can certainly just look at the leading coefficients, 1 over 2. That's less than 1. The series converges.